In this lesson, we will study how to solve exponential and logarithmic equations. Let's start with an exponential equation. We have 4 to the power of x minus 2 is equal to 64. Now, the first method I will show you is getting the same base on both sides of your equation. The base here is base 4. So my goal, my strategy is to rewrite 64 as base 4, as having the same base as the left-hand side. Now we must understand that 64 is 4 cubed. Okay, 4 times 4 times 4 is 64. And so what we can say now is 4 to the power of x minus 2 will be equivalent to 4 raised to the power of 3 if and only if the powers are equivalent. This is the only way that the left-hand side will be equivalent to the right-hand side. They have the same base, so the only way you're going to have equivalence here is if x minus 2 is equivalent to 3. This power is equivalent to this power. So now we dropped the bases, we got rid of the common bases, and we just set the exponents equal to each other. And now I have a linear equation. All I have to do to solve here for x is to isolate x by adding 2 to both sides, and I get x is equal to 5. And this is my solution. X is equal to 5. And you can plug this in, of course, to the original equation to confirm. And let's do it in our minds here. If you plug in x equal to 5, it'll be 5 minus 2. And 5 minus 2 is 3. 4 raised to the power of 3 is indeed 64. So for the first few examples that we will go through today, we'll use this strategy over and over again, getting the same base on both sides. Here's a new example. 5 raised to the power of x squared minus 4x is equal to 1 over 125. Okay, the left-hand side is base 5, and I do know that the number 125 is 5 cubed. I can rewrite this as 1 over 5 cubed. So I'm going to use strategy number 1 again. I'm going to get the same base on both sides. Okay, so I'm getting the same base. I rewrote 125 as 5 cubed, but I can do even better than this. I can rewrite the right-hand side as 5 to the power of negative 3, right? And so now that you have the same base, what we can do is drop the bases and set the exponents equal to each other. This is x squared minus 4x must be equal to negative 3. Okay, at this point, this resulting equation is quadratic, and the way I solve quadratics most of the time is by setting it equal to 0. So let me add 3 to the left-hand side. All right, very good. And at this point, you can try to factor it, or you can use a quadratic formula, or you can complete the square. I'm going to factor, and it factors as x minus 3 times x minus 1 is equal to 0. I'm going to set each of my factors equal to 0 and solve, and I get two solutions here. X is equal to 3 or x is equal to 1. All right, very good. I hope this is going smooth for you so far. So far we've seen two examples, and we use the same strategy for both of them. We got the same base on both sides. Here's a third example here. We have 6 to the power of x is equal to 8. Now, strategy number 1 is not going to work here because we're not going to be able to get both the same base on both sides. I mean, the best you can do is rewrite 8 as base 2, maybe. 8 is 2 to the power of 3, but 6 is not going to be rewritten as base 2. So we're not going to get the same base on both sides. So we're going to have to use a different strategy. This second strategy is taking the log or logarithm of both sides. Now, remember the power rule for logarithms. I'll remind you of the power rule right here, right now. The power rule that we learned in a previous lesson said log base b of m to the power of p is equal to p times log base b of m. So in other words, this is your exponential expression, m to the power of p. And if you're taking a logarithm of an exponential expression, the power comes down to the front like this. So if I had log in front of 6 to the power x, my exponential expression, then the power of x would come down to the front and I can isolate x and solve for it. So that's my strategy. I'm going to take log of this left-hand side so that I can solve for x. But if I take the log of the left-hand side, of course, we have to take log of the right-hand side. Now, when I say take log of both sides, it doesn't matter what kind of base you take of both sides. A log base, 10 of both sides is what I'm doing. I'm doing a common log of both sides. You're probably going to want to use common log most of the time, or the natural log of both sides. If you ever needed an approximation of your answer, it's convenient to take the common log or the natural log of both sides because our scientific calculators can evaluate common logs and natural logs. So when you log both sides, do common log of both sides or the natural log of both sides. Now the power rule here for logarithm says x comes down as a coefficient, right? So now I have x times log of 6 is equal to log of 8. So now I see all I have to do to both sides is divide by the number log 6. Divide by the number log 6. Remember, it's just a number. It's an exponent. A logarithm is an exponent. So log 6 is the exponent to which you raise 10 to get 6. The exponent to which you raise 10 to get 6. So this is just a number. Which number is it? Well, I could give an approximation without a calculator. 10 raised to the 0th power gives me 1. 10 raised to the first power gives me 10, correct? The exponent to which I would raise 10 to get 6 must be between 0 and 1, right? If raising 10 to the 0th power gives me 1, and raising 10 to the first power gives me 10, then 10 raised to a fraction between 0 and 1 would give me an output of 6. So I know that this number must be some kind of fraction, right? Some type of decimal that is between 0 and 1. Anyway, it's just a number. So we're dividing both sides by a number, okay, to isolate x. Now, we know that what happens as a result is those two divide out. And so your exact answer is log of 8 over log of 6. This is important that you understand that this is an exact answer. When you're solving these equations, you want to get an exact answer, Sometimes it's helpful to get an approximation. So if you punch this into your calculator, it'll give you an approximation. And rounded to 4 decimal places here, it is approximately 1.1606. That's what this answer is approximately. I encourage you to practice punching this into your calculator and confirming that you can get this approximation. All right, so this was our first example where we had to change up our strategy, right? We had to take log of both sides because getting the same base was not working, all right? So let's look at another example now. Here's our next exponential equation. We have 3 to the power x plus 4 is equal to 2 to the power x. Now, strategy 1 is not going to work here, which is getting the same base on both sides. I mean, the base on the left-hand side is the prime number 3, and the base on the right-hand side is the prime number 2. So strategy 1 will not work, but strategy 2 will. I'm going to log both sides. Now, I'm going to choose to do the common log of both sides. That's what I do most of the time. Okay, most of the time is take the common log of both sides. Okay, now what this does, it allows your power to come down. Using the power rule for logarithms, we have x plus 4 times log of 3. Now remember, you have to have parentheses around x plus 4 because this is more than one term that you're bringing down. is equal to x times log of 2. Remember that the base of your logarithms is 10. All right, cool. What I'm going to do now is distribute this number, log 3. This is a number, right? So this is the exponent to which you raise 10 to get 3, okay? It must be some decimal that's between 0 and 1. All right, so what we have now as a result is x times this number, log 3, plus 4 times this number, log 3, is equal to x times log 2. Now let's remind ourselves what it is we're doing. We're solving for x. So the way you solve for x here is by isolating x. That is to say, getting all of your x terms on one side of the equation. So I suggest you subtract x log 3 from both sides so that both of your x terms will be over here on the right. So I will subtract x log 3 from both sides. And what I have as a result is, now allow me to rewrite, allow me to write the right-hand side first, okay? I'm going to write this side first. So I'm going to have x log 2 minus x log 3 is equal to 4 log 3. Now please notice that these two terms on the left both have an x. So what I'm going to do is I'm going to factor out the x from both of those terms. Now, when you factor an x out of the first term, you're just left with log 2, the number log 2. And then the second one, you're just left with minus log 3. Now remember, all of this is just one number being subtracted from another, right? So all of this is a number. So then with that being said, to solve for x, all you have to do is divide both sides by this number, whatever log 2 minus log 3 is, right? That's what we're dividing both sides by. Now, we already know that this number divided by itself is just 1, right? So on the left-hand side, you have x isolated. And so x is exactly equal to 4 log 3 divided by log 2 minus log 3. This is the exact answer, okay? Now, I would encourage you to practice punching this into your calculator and getting the approximation that x is approximately equal to negative 10.8380. Okay, so practice doing that. When you punch this into your calculator, folks, you're probably going to have to type in 4 log 3 first and then punch divided by. And then you're probably going to have to open up a set of parentheses right after you punch division. Open up a set of parentheses and then put log 2 minus log 3. Close the parentheses and then press equals. So practice doing that and getting this decimal. This is the last exponential equation that I wanted to show you. It's e to the power of 3.5x is equal to 42. Keep in mind we're solving for x, okay? E is just a number like we learned in an earlier lesson. Strategy number 1 is not going to work, getting the same base on both sides. After all, the left-hand side is base e. The strategy number 2 will. We're going to take log of both sides. Now, watch this. We have been taking a common log of both sides. Common log, right? That's just what I do. It's most of the time what I do. But because the left-hand side is base e, I'm actually going to take the natural log of both sides. It's going to work out really nicely, and you're going to see in just a second why the natural log would be really helpful. Okay, so I'm taking the natural log of the left-hand side, and I'm taking the natural log of the right-hand side. Whenever I'm solving an exponential equation and I see base e, I always take the natural log. Okay, now, by the power rule for logarithms, we know that the power rule comes, the power comes down. All right, there we have it. Now, here we go. The natural log of e, remember that natural log right here, ln, means log base e. Log base e. So this logarithm is asking you for the exponent to which you raise e in order to get e. right? This is log base e. So what exponent do you raise e to in order to get e? 1. So natural log of e is just 1. That is the reason why I took the natural log of both sides, so that the natural log of e would basically turn into 1, which is now it's just gone, right? So that simplified really nicely. So just please remember, make sure you write in your notes, whenever you have an exponential equation with base e, take the natural log of both sides. Okay, so we're going to divide both sides in order to solve for x. Divide both sides by 3.5. So your exact answer is the natural log of 42 divided by 3.5. Okay? Punch this into your calculator and get an approximation, please. Just for practice sake, you should be getting the number approximately 1.0679. All right, everybody, now let's transition to logarithmic equations. Here's the first log equation I have us solving. Log of 25x is equal to 2. Now, our strategy here is to rewrite this log equation as an exponential equation. Now, I showed you how to do this in an earlier lesson. You take the base, which happens to be 10 in this example, you raise it to this power of 2, and that gives you the argument of 25x. So the equivalent exponential equation would be 10 squared is equal to 25x, or 100 is equal to 25x. So if we divide both sides by 25, we get our answer that x is equal to 4. And then you're done. That's it. This is the solution, x equal to 4. For log equations, it's very, 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 very important that you always check your answer. All right, so when you plug in 4, 25 times 4 is 100. 100 is what you get when you take 10 and you square it. So it definitely satisfies the original equation. Okay, so this is going to be our strategy. Whenever you have a logarithm set equal to just a number like this, one logarithm set equal to a number, a constant, then just rewrite it as an exponential and then solve. Check this one out. Log of x plus log of x minus 21 is equal to 2. Now, I cannot change this to an exponential by doing, this kind of work like that. I can't do that yet because I don't have just one logarithm on the left. I have a sum of logs. But the good news is you and I studied in a previous lesson how you can rewrite a sum of logs as a single log using something called the product rule for logarithms. So it would be one single log, and then you would take the arguments and multiply them. I hope you remember this product rule for logarithms. So now that you have just one logarithm set equal to a constant, I can now rewrite this as its related exponential equation. So this is base 10 again, so this is going to be 10 squared is equal to x times x minus 21. This resulting equation is going to be quadratic because you're going to have 100 is equal to x squared minus 21x. Because it's quadratic, I'm going to subtract 100 from both sides so that I can set this equal to 0. So I subtracted 100 from both sides. Because it's quadratic, you can use the quadratic formula. You can try to complete the square, or you can try to factor. I'm going to try to factor this. It will factor as x minus 25 times x plus 4. And I will set each factor equal to 0 and solve. So I'm getting two proposed solutions, either positive 25 or negative 4. Now, I said earlier that it is crucial that you check your solutions. These are proposed solutions in the original equation. I can see right now that when I plug in -4 in for x, I get log of -4. Go ahead and stop right there. There's not even a need to go any further. You cannot, the argument cannot be negative. And when you plug in -4 right here, and actually right here as well, the argument becomes negative. And so this would be undefined. So this does not work. Okay, so then what that means is this, and we learned this in an earlier lesson, that this solution here is called extraneous. X equal to -4 is an extraneous solution. It satisfies the manipulated equation, but not the original. Okay, it satisfies the manipulated equation, but not the original. Now what you're going to see me do is check 25. So you're going to have log of 25 plus log of 25 minus 21 is equal to 2. Honestly, folks, all I'm really checking is to confirm that my arguments are non-negative, and they are non-negative. Look at this is not negative, and neither is this. So I'm just going to go ahead and stop and say, yep, it works. X equal to 25 is my one and only solution. So you may want to write in your notes, for log equations, make sure you check your final answers for any extraneous solutions. Check out this log equation. Log base 2 of 11 minus log base 2 of x is equal to 10. Now, once again, my strategy is going to be the same, which is to rewrite this as its related exponential equation, but I am not allowed to do this yet, right? I cannot change it to its related exponential equation until both of these logarithms, this difference of logs, becomes one logarithm. So you can see what we keep wanting is only one logarithm on one side of the equation and set equal to a number, right? Now, I hope you remember the quotient rule for logarithms from an earlier lesson. The quotient rule for logarithms says that you can rewrite a difference of logs as a single logarithm, as a single log. And the way you do that is 11, which is the first argument, is the numerator of your new argument, and x, which is your second argument, becomes the denominator of this new argument. Okay, so that was the quotient rule right there for logarithms. Now that we have one single logarithm set equal to a constant, now I can rewrite this as its related exponential equation. Base 2 raised to the power of 10 is equal to 11 over x. Okay, I believe 2 to the power of 10 is 1,024, right? You can use your calculator for that. Is equal to 11 over x. This resulting equation happens to be rational. What I want to do is multiply both sides by x. Okay, because I'm trying to solve for x. So these x's here divide out, right? And what you're left with is 1,024x is equal to 11. Of course, don't forget that you're trying to isolate x, right? So divide both sides by 1,024. And so your final answer is, well, it's a proposed solution, is 11 over 1,024. This is a positive number. Let me go to the original equation, which is here. This is the original. And notice that when you plug in a positive number for x, it's, this is the only place where x is. The argument is positive, right? So in other words, when I do log base 2 of 11 minus log base 2, right here, of 11 over 1,024, this is valid because the argument is positive, of course, because you're plugging in a positive number in for x. So I know right now that plugging in this solution does not give me a negative argument, so this is valid. So this here is my one and only solution. So I hope you see the strategy for solving log equations. Rewrite the the equation so that you have one logarithm and then rewrite that log equation as an exponential equation. For your notes purposes, I think it's nice to have these words actually written down. If necessary, use the product or quotient rule to rewrite the log equation with a single log. That's what you want all the time. Then rewrite the log equation as an exponential equation. And then you can go ahead and solve that resulting equation, whether it's linear, quadratic, or whatever have you. Now this is the last log equation that we're going to look at in this lesson. And it's different than the others. It's different than the others because you have a logarithm on one side and a logarithm on the other, okay? And so what I am going to recommend is that you get both of the logs on the same side. So maybe subtract this one from both sides, like this. And then you would have log of 7x plus 1 minus log of 6x minus 5 is equal to 0. Now that you have two logs on the same side, now just follow the strategy that we wrote down a minute ago. Here we're going to use the quotient rule. The quotient rule, because it's a difference of logs, as a single logarithm, okay? The quotient rule for logarithms will say this is equal to log of 7x plus 1 over 6x minus 5 is equal to 0. And now that you only have a single log, we can rewrite this as its related exponential equation. The base is 10, so it'll be 10 to the 0th power is equal to this argument. Okay, so now at this point, it's just like all the others, right? Same kind of format here. And so then we have 10 to the 0th power is equal to 7x plus 1 over 6x minus 5. Or 1 is equal to 7x plus 1 over 6x minus 5. Now, in order to solve for x here, I think we want to multiply both sides by 6x minus 5. Right-hand side like this, and that'll get these to cancel out entirely. Don't forget to multiply the left-hand side also by 6x minus 5. 6x minus 5 times 1, of course, is just 6x minus 5, and the right-hand side is just 7x plus 1. When you solve for x here, maybe you want to subtract 7x from both sides. I'm not sure. That will leave you to negative x minus 5 is equal to 1. And then maybe at this point, add 5 to the right-hand side. Okay. And this will lead you to negative x is equal to 6. And then finally, divide both sides by negative 1. And then you get x is equal to negative 6. Now, let's go back to the original original equation, and confirm that this solution is indeed valid, and make sure it's not extraneous. So here I am plugging in my proposed solution into the original equation, okay? And I'm noticing right now, as I'm writing this out, that my arguments turn negative. I mean, this is negative 41, right, is equal to log of negative 41. But, you know, although the left and the right-hand side are the same, this is not okay, right? It's not okay to have a negative argument, or else your logarithm is undefined. So what that tells me is this solution, x equal to negative 6, must be extraneous, an extraneous solution. But wait a minute. The one and only proposed solution that the algebra provided does not satisfy the original equation. The only answer that I found actually doesn't work. That must mean my final answer is just no solution. This was the first equation that we looked at that had no solution, all right? So just before we end this lesson, just want to reiterate, whenever you have a log equation, make sure you check your answers, right, for extraneous solutions. All right, everybody, I hope you enjoyed solving exponential and logarithmic equations. Just a little summary. For exponential equations, we either got the same base or we logged both sides. For log equations, our strategy was to rewrite the log equation as an exponential equation. But before you do that, you have to have a single log. All right. Happy studying. I'll catch you later.